So we start double integration. This is the first of the multiple integrations. We have double integration, triple integration, and so on. You may have nth order integration for any n. So what's the motivation for a one variable function y equals f of x? The integration a to b f of x dx is the area. It's the area of the region between the graph of y equals f of x and the x-axis, provided that f x is positive on AB. And f is a reasonable function. So what we mean is this. Suppose we have a region like this, and we have a reasonable function. What we mean, for example, a continuous function. Actually, it doesn't have to be continuous, but it should be something nice. And if you have a graph like this, then the integration from a to b of f of x is just the area of this region. Okay, y equals f of x. So double integration in that sense is the one-dimensional higher version of this. Namely, now let z equals f of xy be a function defined on a closed and bounded region. Then we may try to compute the volume of the solid region bounded region. Bu region'a bir isim verelim. Region D diyelim. Solid region above D between the graph of z equals f of xy and the xy plane. So here is what we mean. Suppose we have xyz coordinate system, and we have some region D, and we have a graph. Okay. Şöyle diyeyim. Okay, z equals f of xy, and we would like to compute the volume of the region bounded below by the xy plane and above by the graph of z equals fxy, a surface over this region D. Okay, so suppose you have a region on the table and you have a graph here. So above this region and below this graph there is a certain volume, and you would like to compute that volume. Okay, so double integral is a way of computing this. How? Well, you do this as if we do in the first one variable case. What was the uh, definition of integral in the one variable case? Well, we do the following. Right? If you have a function like this, what you do, you divide this interval into pieces. I'm sorry. N pieces, let's say, starting with x0, x1, x2, x3, and xn. The lengths of these intervals doesn't have to be even the same, okay? And then what you do from each interval, so you look at this regions, okay, şöyle çizeyim, okay. Okay. Here, let's say we have xi and xi plus 1. From each sub-interval, we choose some point, let's say xi star, okay, and then you compute your function at this point. So this point is what? This point is x coordinate is xi star and y coordinate is fxi star, and then you multiply this length and the value of this function, so you compute the area of this region, right? So what's that area? It is f of xi star, this is the height, and then the base length. Base length is xi plus 1 minus xi, right? So this is just the area of this rectangular region. And then you just do this same for each subinterval. So you pick here points x1 star, x2 star, and so on. Okay? And then you just add them up. You just add them up. I from 0 to n minus 1. So that when I is equal to n, you are at this point. Okay? Because here you have xi plus 1. So this is an approximation, for the area below the graph of y equals f of x above the interval AB. This is an approximation. And what is the Riemann integral? Riemann integral is the following. You just keep doing this for all partitions of AB. So you have this interval AB. You divide this into n pieces. It doesn't have to be same, size, xi plus 1. And you call the, what was it, mesh. So P is the following. This is x0 is equal to A. And then you have x1 up to xn. And this is B. Okay. So you pick points like this. And the mesh of, so this is the norm of the mesh is just the maximum of xi plus 1 minus xi. So you measure these distances. You call the maximal one to be the norm of this partition. So norm of the partition, the norm of the partition P. And then you do the following. You compute this sum for all partitions. And so you compute this for all partitions. And you take limit as p goes to 0. What we mean, I choose each time partitions with greater n values. So first I divide this into, let's say, 10 pieces, and then 12 pieces, and then 20 pieces, and so on, so that this length goes to 0. Okay. And then I compute this expression for each p, and then if this limit exists, we call it the integral of f. So this is by definition the integral of f from a to b, provided that the limit exists as p goes to 0. And we have a theorem. Okay, in this case, we say that f is integrable over AB. Okay. We have a theorem. For example, we know that if f of x is continuous on AB, then f is integrable over AB. This is something you have seen in first variable calculus. What we will do, we will just mimic this in 2 dimensions. Instead of partitioning the interval into subintervals, we will partition the region into subrectangles. Okay, in 2 variables, we will mimic the same construction. as follows. Şimdi anlatayım size nasıl yapacağımızı. Suppose D in R2 is a reasonable region. What's a reasonable region? Well, I will not tell you about that. Actually, anything you can consider is reasonable. But in general, this D can be very weird. I will talk about those. But anything you may consider right now, something like this, or this, or something like this with some holes. These are all reasonable regions, but there are some regions where things are really complicated. I will talk about them later. We divide, so this region, suppose we have this region over here. Okay, we divide this region into not intervals but rectangles. How? Well, like this. Okay, and then okay, şöyle yapayım. Şuradan da şöyle böldüğümüzü düşünelim. And so suppose our region is like this, and we have a partition of this region into intervals like this. And suppose this is x0 is equal to, let's say, some a, x1, x2, xn equals b, and here I have y0, let's say c, y1, ym equals d. So over the rectangle AB cross CD, so I have this rectangle here. So my region D is inside AB cross CD, okay, and AB is divided into these intervals x1, x2 up to xn equals B, and CD is divided into intervals m intervals like this, okay, and on each rectangle, if the rectangle intersects with D, I will pick up a point from that rectangle. Okay, let me choose this color. So from each rectangle, I will pick up a point like this. And what are the coordinates of this point? Let's say this is xi star, yj star. Okay, so we pick a point, let's say xi star, yj star. Xi star is between xi and xi plus 1, and yj star is between, okay, sorry, yj and yj plus 1. yj plus 1. Okay. And then, so I have this subrectangle here. Okay, subrectangle. Here, this is xi plus 1, yj plus 1. And here I have this point, xi star, yi star. Over this rectangle, we have our, let's say, region, something like this. This is the graph of z equals fxy. What I do, I compute my function at this point. This is the height. So what is this point? This point is xi star, yj star, and then f of xi star, yj star. And I consider the rectangular region with base, this rectangle, and height this much. So these are the base lengths and this is the height. What is the volume of this? Volume of this rectangular box is just xi plus 1 minus xi, yj plus 1 minus yj, and then the height, right? Height. And then let me call this volume ij, okay? Volume of ij. And then we just add these volume ij's over I from 1 up to n and j from 1 up to m. This is an approximation, for the volume of the solid region bounded from above by the graph of z equals fxy and below by the xy plane. On the bottom you have the xy plane, and on the above you have this curved region, surface, z equals fxy. So it's something like this. This is xi plus 1, yj plus 1. Over this you have some graph. And to compute the volume of this object, what I do, I pick a point here, compute the height of the function at this point, and then I consider the rectangular box, and I take the volume of this rectangular box as an approximation for the volume of this region, whose bottom side and this sides are plane regions, but the top is a curved surface. Okay, so this is an approximation for that volume. And what is the integral? Integral is the following. You just keep doing this operation for smaller and smaller intervals. So you divide you divide the region into smaller pieces in x and y direction, and then you take limit as this length goes to 0. If that limit exists, then we say that that limit is the integral of f over this region. So what we do, we just take limit. Okay, by the way, what is the so p is this object. P is what? P is the following. You divide, so you have xi yj's. such that x0 is equal to a, or a is equal to x0, x1 up to xn, which is b, and yj's are this. C is y0, and then y1 up to ym, which is d. So you divide x interval and y interval into pieces. The norm of this partition is the following. It is the maximum of the diagonals. So it is the maximum of what? The following. Xi plus 1 minus xi squared plus yj plus 1 minus yj squared. So you have this box here, xi plus 1, yj plus 1. You measure this diagonal and take the length of this diagonal, and then you take maximum of all these diagonals. So it's the size of this rectangle, değil mi? Televizyon ekranı da bu şekilde, değil mi? İşte 42 ekran demek diagonalin ölçüsüdür. Aynı o şekilde. So you just do the following. You take limit over all this piece as this length goes to 0 of what? F of xi star yj star xi plus 1 minus xi yj plus 1 minus yj. I from 1 up to, let's say, n, j from 1 up to m. Okay. As p goes to 0, of course, both n and m goes to 0. Goes to infinity, değil mi? Yani en büyük uzunluğu sıfıra gönderirseniz o zaman yaptığınız bölme sayısının da giderek artması lazım. Hem x yönünde hem y yönünde bu uzunluklar sıfıra gittiği için, ama belli bir uzunluğu kaplaması lazım. O yüzden de p sıfıra giderken p'nin normu n ve m sonsuza gidiyorlar. Bu integral eğer varsa, pardon, bu limit varsa, if this limit exists, then we say that f is integrable over the region D. And write the following. The double integral of f xy dx dy is equal to this limit. Partition sıfıra giderken, evet. Yj. Burada where xi star and yj stars are arbitrarily chosen. In the intervals xi plus 1 and yj plus 1 respectively. Yani bu noktaları da rastgele seçiyorum. Her seçim için bunun doğru olması lazım. Tamam mı? Nasıl seçerseniz siz. No matter how you choose these points, this limit should exist. Okay? What about a rectangle like this? Here, I mean, if you have a rectangle like this, then you don't take this into account because your function is not defined here. But if it is like this, then you take this into account. Okay. If your region doesn't intersect with some of the subrectangles, then you don't take that one into account. Or you may just take your function to be zero at that point. Tamam mı? Yani fonksiyonunuz burada tanımlı değil ama bu integralin anlamlı olması için fonksiyonu burada mesela sıfır diye tarif edebilirsiniz. Tamam mı? Dolayısıyla bu bölgeler işin içine girmeyecek. So this is the basic idea of double integration. So it is just one dimensional higher version of a single variable integration. Okay. This object here, the sum in the above definition is called a Riemann sum for the integral of fxy over the region D. Peki, benim verdiğim tanım kitaptakinden hafiften farklı şekilde state edilmiş ama aynı şey. Teorem de şu. As in the one variable case, if your function is continuous, and if the region D is a nice region, what we mean is the following, then the function is integrable. If f of xy is a continuous function on a closed bounded domain D, whose boundary consists of finitely many curves of finite length, then f is integrable on D or over D. Burada ne kastediyoruz? Closed bounded region. Boundaries'te finitely many curve'den oluşuyor. Yani region şöyle bir şey. This D is something like this. It may have some hole in it. So our region is D, something like this. Okay, D. Boundary consists of several curves. Each one should have finite length. You may think, are there curves of infinite length? Well, yes. The curve, you may join this curve, 2 points with a curve of length infinite. How? You can do something like this. Okay, you can arrange this so that you have infinitely many up and downs, and the length of each piece is 1 over n. Then when you add them up, you get infinite. Okay, so you may have uh, some boundary curves of this type. In that case, the integral may not exist. Okay, if there are infinitely many up and downs, and if the boundary this curve can be continuous even, but it may have infinite length. Okay, infinite length. So there are very crazy curves. Here we assume that our D, region D, doesn't have such curves on the boundary. Okay. Okay. We will not prove this theorem because uh, the proof uses mathematical analysis, which you haven't seen so far. That's why we just omit it. But as you realize, this is just the two-dimensional version of single variable uh, functions, right? There we had if f of x is a continuous function on some interval ab. Here, ab is just an interval. It cannot be something weird. Then this integral exists. A to b exists, right? If this is continuous, then this integral exists. So this is just the two-dimensional analog of this result. But here, instead of this interval, we have a region, and then things get complicated. Okay. Now, this is how you define integral, but how you compute it is another, of course, story. Let's see that properties of the double integral. Sorusu olan var mı? Kavramsal olarak şurası anlaşılmadı. Ne menem şeydir bu falan diyorsanız sorabilirsiniz. Okay. Şimdi integration'ı hesaplamak için bir takım yollar var. Onların bazılarını söyleyeceğim. Suppose f and g are integrable functions over some region D, and L, M, N are constants. Then we have the followings. Again, these properties are analogous to those properties for a single variable integration of single variable functions. Namely, we have this first. The double integral of f xy şurada bir dakika şu notasyonda şunu dx dy değil de dA diye yapayım. dA dediğim şey de şuna karşılık geliyor. Tamam mı? Hani area. In one variable case we had dx length, but here this is the area element. Area element. We call it area element. So it is like dx dy. Actually, I'll talk about it in a minute. But here, let me write dA. This is 0 if d has uh, zero area. So if D has zero area, then this integral is zero. It's like, if you have length of an interval zero, right? It's like, integral over from 2 to 2 f of x dx, right? This is just zero because the length of the interval is just, the interval is consist of single point, and this integral is zero. So it's analogous version of that. Area of a domain, this is the area of the D, area of D. Why is that? This is simple. I mean, you have this region D, and area of this is the same as the volume of the right region. Uh, okay. Şöyle yapayım. Pardon. D olsun. If the uh, height is 1 unit, like this one, then the volume of this, right? What is the volume of, let's say, V of this region? Well, it is just area of D, right? Because the height is 1 unit. So that's basically this fact. Uh, if you integrate the function, constant function 1 over a region, if this integral exists, then that is the volume of this object. But this object, the volume of this object is nothing but the area of its base, right? Because the height is 1 unit. Third one, yeah, sure. Actually, we will just talk about it in a minute. We can take constants out. So what you are saying comes to that. So integrals representing volumes. What we mean is this: if fxy is positive on D, then this integral, as we discussed, right, dA is equal to V, where V is the volume of the solid lying vertically above D and below the surface z equals f of xy. Yani üstte e, grafiğimiz var, yüzeyin grafiği. Aşağıda da eksi y düzlemi var. Fonksiyon hep pozitif değerler alıyorsa, yani grafik x y plane'in üstünde ise, bu D bölgesinin üzerinde kalan parçanın hacmi işte bu integral oluyor. Aynı şeydeki gibi değil mi? One variable'da da işte şuradaki bu alana karşılık geliyordu integral. Burada da volume'a karşılık geliyor double integralde. Aynı şey. Okay. The Tabii ki if fxy is always negative on D, then this integral fxy dA is minus V. This is a negative number. Where V is the volume between the graph of z equals fxy and the xy plane. This time region is below the xy plane. Integral will be a negative number because these are all negative numbers. You take negative numbers, multiply with the base area, still negative, and then add them up, you get negative numbers. But these negative numbers are actually just the sum of the, these are the volumes of the pieces like this, right? Volumes of the pieces like, neredeydi onlar? Volumes of pieces like this, but this region is below the xy plane, okay? Volume is of course positive, but the integral is negative because this is a negative number. These are positive, this is negative. Therefore, this thing is negative. However, its absolute value is nothing but the volume of this object. Okay? Yani şey gibi. In two-dimensional case, what does this correspond? You have a graph like this, right? The integral of this is nothing but this area multiplied with minus 1, right? This integral is not the area. Its negative is the area. So the same analogy. Okay. Okay. Uh, linear dependence. Linear dependence. Ne demek bu? Integral of L times fxy plus m times gxy dA over this region D is the same as the following. You can break this integral into two parts, fxy dA, and take this constant outside, and same thing over here, gxy dA. Yani integrali içerideki nesne böyle linear combination şeklinde ise toplam ve çarpımlar, toplamları ayırabilirim ve buradaki katsayıları da dışarı alabilirim. İşte senin dediğin gibi bu 5 ise bu 5'i dışarıya alabilirim. Tamam mı? Inequalities are preserved. Namely, if fxy is less than gxy on D at every point of D, then the integral of fxy dA is less than gxy dA. Pardon. Niye böyle oluyor? Değil mi? Bu da şeye denk geliyor. Yani you have one graph and above that you have another graph. Then the area, this area is less than this area, right? In this case, this is for volumes. If you have a bigger function, then the volume above the bigger function is of course greater than the volume below the smaller function. triangle inequality, angle inequality. What we mean is this: if you have a function like this, the absolute value of the integral is less than the integral of the absolute value of the function. Değil mi? Fonksiyonun mutlak değerinin integralin mutlak değerinden büyüktür. Bu one variable'da da geçerli. Neden? Bu şuna denk geliyor. This corresponds to the following. Suppose you have a function like this. This integral is the sum of these areas, but here this is plus and this is minus, so you subtract this area from the sum of these areas. But what about this one? Here it is the following. You take absolute value, so you get something like this. Therefore, this negative turns to be positive when you take absolute value. Therefore, this area is, of course, larger than this area. Okay, so that's the statement. And finally, I have the following. H, if D is the union of regions like this, it's the union of non-overlapping regions, so that f is integrable over each di, then the integral of f over d is the sum of integrals of f over di's, I from 1 up to k. Şurada tabii fda yazmam lazım. Fda. Yani eğer bölgemiz birbiriyle kesişmeyen regionların union'ı ise integral over the union is just the sum of the integrals over each piece. Okay, now let's have a break. After the break, I'll continue.